Now, uh, here, last time we have discussed about the plane waves and the properties, reflection and refraction, polarization, phase and group velocity, propagation through various media, okay, and what is meant by the scale depth. Today we'll discuss about that of the transmission lines, equations, characteristic impedance, then impedance matching means what, then impedance transformation, and also the Smith chart and S parameters. Okay, now therefore we will start uh, about that of the transmission line. Okay, transmission line is used to transfer the information or the energy from one point to that of the another point. We are applying the voltage at the input of the transmission line, and that wave is propagated along that of the transmission line, and so that the load will absorb the power transmitted from that of the transfer. Power is transferred from the source to that of the generator, and power is absorbed by that of the load. Okay, now the performance of the transmission line is depends upon the type of the transmission line, whether it is its propagation constant, okay, and characteristic impedance of the transmission line, load applied, and type of the transmission line. Okay, that these are means we can analyze the transmission line. Now, first of all, we have to see that actually what is the equation for that of the voltages and the currents uh, which are exist along that of the transmission line. Okay, now this is the equation for that of the voltage. V is equal to V plus e to the power of minus gamma x plus V minus e to the power of plus gamma x. This is the equation for that of the voltage which will be exist along that of the transmission line. Now here V plus is the maximum amplitude, e to the power of minus gamma into x is the phase. Gamma is nothing but the actually the propagation constant, and the propagation constant is given by this equation. Here you can see that actually the equation for that of the propagation constant, that is gamma is equal to alpha plus j beta. Okay, gamma is nothing but the propagation constant. Okay, uh, here. Now this is the equation for that of the propagation constant, under root of r plus j omega l in another bracket g plus j omega c, or it is also equal to that of the alpha plus g beta. Now here r is nothing but the resistance per unit length of the transmission line. L is nothing but the inductance per unit length. G is the conductance per unit length, and C is the capacitance per unit length. Okay, now this propagation constant is the complex number or complex quantity. Therefore, it is having the real part and the imaginary part. And if we write in the form of the complex number this propagation constant, then we can write as the propagation constant is equal to the alpha plus j beta. Now here alpha is nothing but the attenuation constant. It will measure how at what rate the wave is attenuating, or what speed the wave is attenuating. That information is given by that of the attenuation constant, and its unit is Nepers per meter, or another unit for that of the attenuation constant is the decibel per meter. Now another parameter of the propagation of the wave along that of the transmission line is the phase constant. It is the measure of the how the phase is changing with respect to that of the per unit length, or at what rate the phase is changing. That information is given by that of the phase constant, and it is measured in radian per meter. Okay, that rate of change of the phase is denoted by that of the phase constant. Now the wave is traveling along that of the transmission line. Now if you see the solution of the transmission line, then it have two parts. That is the first part is the forward wave, and second part is the reverse wave. Okay, and therefore you can also see that here basically when when we will get the equation for that of the voltage, then that equation have two parts. Now here you can see that. Okay, now this is the equation for that of the voltage. Now this is the first part and this is the second part. Okay, now this equation for that of the voltage is formed by that of the two terms. You can say that is the first term represent actually the forward wave. Now this forward wave is having amplitude v plus, and e to the power of minus gamma into x is the its a phase is also changing with respect to that of the time and also the space. Now the second part or the second term represent actually the reverse wave. Reverse wave means that wave is traveling from that of the load to the generator. Okay, therefore this wave is called as the reverse voltage. Okay, similarly there is also the forward current and reverse. Now this is the equation for that of the current, and this first term represent the forward current, second term represent the reverse current. Okay, now therefore now this Z naught represent actually the characteristic impedance of the transmission line. Now the characteristic impedance is nothing but the ratio of the voltage to that of the current. You know that the impedance is just the ratio of the voltage to that of the current, and this characteristic impedance we can also find out, and its equation is, now we have already obtained the equation for that of the voltage and the current. Okay, that is the equations of the transmission line. Okay, and okay, here you can see that how it is obtained. That is the characteristic impedance is nothing but forward voltage to that of the ratio of the forward voltage to that of the forward current. Then you will get under root of r plus j omega l. Now here is actually forward current, I plus will be there. Okay, now therefore you will get it is under root of r plus j omega l divided by g plus j omega c, and there is also the characteristic impedance is observed by that of the reverse wave. Now there may be for that of the reverse wave will observe the characteristic impedance minus z naught. Okay, because there is the ratio of voltage, reverse voltage to that of the reverse current, and you will get the equation same, that is the under root of r plus j omega l divided by j omega c. Now this is the equation for that of the characteristic impedance. Okay, at any location of the transmission line you will get the characteristic impedance Z naught. Now this characteristic impedance, if you observe the equation for that of the characteristic impedance, now this characteristic impedance is depends upon that of your resistance per unit length of the transmission line, then inductance per unit length of the transmission line, that is distributed parameters of the transmission line, and also the angular frequency of the signal which is traveling along that of the transmission line. Okay, now therefore this is the equation for that of the characteristic impedance of the transmission line. Now there are two types of the waves, that is the forward wave and reverse wave, and backward wave is traveling from load to that of the generator, and its characteristic impedance is negative. Negative indicates that the energy is not supplied but energy is received by that of the generator. Okay, that is the backward wave supplying the energy to that of the source irrespective of the boundary conditions. Okay, backward wave C minus Z naught characteristic impedance. Okay, now therefore here is actually the I plus, and this I plus is replaced by that of V plus divided by Z naught. Therefore you will get actually this amplitude of the forward current, and this is the maximum amplitude of the reverse current V minus divided by Z naught. Now these are the equations for that of the voltages and the current for the transmission line. Okay, forward wave and reverse wave exist. Now the characteristic, we have seen the equation for that of the characteristic impedance also, the equation for that of the voltage and the current for the transmission line. Okay, now these are the equations for the voltages and the current along that of the transmission line. Here you can see that actually this is the generator and this is the load, and here L is equal to 0, and when we move from that of the load to generator, this L is positive, and to this side actually the L is uh, negative. Okay, now here you can see that V is equal to V plus e to the power of gamma L plus V minus e to the power of minus gamma L. This is the equation for that of the voltage. Now gamma is nothing but actually the propagation constant of the transmission line. Okay, now I is nothing but I is equal to V plus divided by Z naught E into e to the power of plus gamma L minus V minus divided by Z naught e to the power of minus gamma into L. Okay, now this is the characteristic impedance of the transmission line. Characteristic impedance and the equation for that of the voltage and the current along that of the transmission line. Okay, now we have to define the reflection coefficient means what. Okay, reflection coefficient is just the ratio of the reflected voltage to that of the forward voltage, and when L is equal to 0, then the equation for that of the reflection coefficient is V minus divided by V plus. Now this reflection coefficient is also the complex number is having the phase and also the magnitude. And when the reflection coefficient is 1, means that total power is reflected back to that of the source, and when reflection coefficient is in between that of the 0 and 1, means some part of the wave is, some part of the power is reflected back and some part of the power is absorbed by that of the load. Okay, suppose that the uh, reflection coefficient is 0.5, means that actually 50% power is reflected back and 50% power is absorbed by the load. Okay, now there is relation between that of the reflection coefficient and the load impedance. Now you can see that reflection coefficient is equal to, in terms of the characteristic impedance and the load impedance, is given by ZL minus Z naught divided by ZL plus Z naught. Okay, now this is the equation for that of the which will give the relation between the load impedance and the characteristic impedance and the reflection coefficient of the transmission line. Okay, we have to remember these equations. Sometimes numerical may be asked. Okay, or here then reflection coefficient we have defined. Then what is means by the matching condition also we have to see. Okay, matching conditions means actually when the characteristic impedance is equal to that of the load impedance, then we can say that that is the matching condition. In such when you can see that actually when Z naught is when ZL is replaced by that of the Z naught, then the numerator will become 0 and this reflection coefficient will become 0. When reflection coefficient is 0, means that the total power is absorbed by that of the load. Okay, there is no reflection by the when reflection coefficient is 0. At that time the total power is absorbed by the load, or reflected power is 0 by this matching condition. Okay, now there is no reflection of power from that of the load. It is called the matching condition. It is similar to that of the maximum power transfer theorem. Okay, now we can also write the equation for that of the voltage and the current in terms of the reflection coefficient by making some arrangement, and these are the equations for that of the voltages and the current uh, in terms of reflection coefficient. That is V of L is equal to V plus e to the power of gamma in bracket 1 plus gamma 1 plus reflection coefficient, and I of L is equal to V plus divided by Z naught e to the power of gamma L 1 minus reflection coefficient. Now these are the equations for the voltage and the current in terms of reflection coefficient. Okay, uh, now then there is also, now we have to see the we have seen this equation. Now that is the equation for that of the reflection coefficient in terms of the load impedance and Z naught. The load impedance means the impedance at the load at the end of the transmission line. That impedance is called as the ZL, or it's also called as the load impedance. Now we have to see the equation for that of the impedance transformation equation. Okay, now the impedance transformation equation is this one, that is Z of L is nothing but actually this is the equation for that of the impedance transformation. Means at any location you can find out the impedance. Now here location is L, that is nothing but a distance L from that of the L units or L meter from that of the load, that is Z of L. At that particular location we are finding the impedance. Okay, that is Z of L is equal to Z naught in bracket ZL cos hyperbolic gamma L plus Z naught sin hyperbolic gamma L divided by Z naught cos hyperbolic gamma L plus ZL sin hyperbolic gamma L. Okay, this is the impedance equation for that of the impedance along that of the transmission line. Okay, now here cos hyperbolic gamma L is nothing but e to the power of gamma L plus e to the power of minus gamma L divided by 2. Sin hyperbolic gamma L is equal to e to the power of gamma L minus e to the power of minus gamma L divided by 2. Okay, now this is the equation for that of the impedance along that of the transmission line. Impedance at location L is the relation to load impedance, and this is the relation. This relation is called as, means there is the relation to that of the load impedance. When we are finding the impedance at any location, at that time there is some relation with that of the load impedance. From this equation we can understand. Okay, now this is the relation. This relation is called as the impedance transformation relation. Okay, now if line is terminated to ZL, the input impedance measured at the input is different, and it is depends upon that of the length of the transmission line. Okay, means that if the depending upon that of the load impedance connected to that of the transmission line, the input impedance is also depends. Okay, and it will depends of input impedance of the transmission line is also depends upon that of the ZL. It is also depends upon that of length of transmission line. Okay, and therefore we will see the equation for normalize the form. Now what is means by the normalize the impedance? When we are dividing the any impedance with that of the characteristic impedance of the transmission line, then we can say that the impedance is normalized impedance. Now the equation for that of the impedance along that of the transmission line in the normalized form is this one. Okay, that is Z of L bar ZL cos hyperbolic gamma L plus sin hyperbolic gamma L divided by cos hyperbolic gamma L plus ZL bar sin hyperbolic gamma L. Here the impedances are normalized. Okay, now ZL is equal to 1, that is nothing but ZL is equal to Z naught, and then ZL bar is equal to 1 and ZL is equal to Z naught. That is the impedance matching condition. When ZL is equal to Z naught, that condition is called impedance matching condition. Okay, now characteristic impedance is that impedance with which its line is terminated. Then impedance is measured at any point on transmission line is equal to terminating impedance. When ZL is equal to Z naught, then if you measure the impedance at any location, you will get it is Z naught only. Okay, at any location if you measure, you will get the same value of the impedance at any location when you terminate, when you connect load impedance as a value of characteristic impedance. Okay, now it is the input impedance of the line on of infinite length. Also, you can say that. Okay, if you try to measure the input impedance of the line of infinite length, then you will get it is the characteristic impedance. Okay, now this is now the equation for that of the transformation equation. We will see that. Now suppose that this is your Z1, that is the impedance at this location is Z1, impedance at this location is Z2, and the distance of Z2 from that of the Z1 is L meter or L unit, you can say that. And if you know the Z1, if you know this Z1 is known to you, and if you want to find out Z2, okay, then how you can find out it? Then by using this equation, it is possible to find out your Z2. That is Z2 is equal to Z naught in bracket Z1 cos hyperbolic gamma L plus Z naught sin hyperbolic gamma L divided by Z naught cos hyperbolic gamma L plus ZL sin hyperbolic gamma L. Okay, because actually you know the characteristic impedance. Actually, whenever any particular transmission line is there, maybe that of the coaxial, maybe that of your twisted pair cable, okay, or any other cables, then it is having some having some characteristic impedance. Okay, that characteristic impedance is nothing but Z naught. We are saying that the transmission line is of 50 ohm transmission line or 300 ohm transmission line or 75 ohm transmission line. Means what? Actually, that is the value of the characteristic impedance of that transmission line. Okay, this is the one of the important parameter of the specification of cable or transmission line, that characteristic impedance Z naught. Okay, now therefore to find out Z2, you should know Z naught, you should know the L, you should know the propagation constant. Propagation constant is means nothing but you should know R, G, L, C. Okay, R is nothing but the resistance per unit length, L is the inductance per unit length, G is the conductance per unit length, and C is the capacitance per unit length. These are the primary parameters of the transmission line. You should know to find out this Z2. Okay, then also suppose that Z2 you have determined. Suppose you know Z2 and you have to find out Z1. Z2 is known means the input impedance of the transmission line is known to you, and you have to find out the load impedance. Okay, then you can find out by using this equation, that is the impedance transformation equation. It is possible to find out the Z1. Okay, now therefore Z1, how you can find out? You know the Z2. You consider that Z2 is the input impedance and Z1 is the load impedance. You imagine. Okay, and then how you can find out this? Z1 is equal to Z naught into Z2 cos hyperbolic gamma L minus Z naught sin hyperbolic gamma L divided by Z naught cos hyperbolic gamma L minus Z2 into sin hyperbolic gamma L. By using this equation, it is possible to find out the impedance. Okay, Z1, Z2 is known to you. Then there are some lossless line means what actually? Lossless lines means R is equal to 0, G is equal to 0. Then we can say that that transmission line is lossless transmission line, and the characteristic impedance as a propagation constant for that of the lossless transmission line is also j omega under root of LC. Okay, and therefore the alpha is equal to 0 for lossless transmission line, beta is equal to omega into under root of LC, and uh, the phase velocity is equal to 1 upon under root of LC. For that of the lossless line, these are the conditions. That is R is equal to 0, then G is equal to 0, and alpha, then you will get alpha is equal to 0, beta is equal to omega into under root of LC. Okay, and the phase velocity is 1 upon under root of LC. Now, the phase velocity depends upon only that of the value of the inductance per unit length and the capacitance per unit length. Okay, V is nothing but the phase velocity. Okay, now the inductance and the capacitance means it is independent of the phase velocity is independent of the angular frequency of the signal which is propagating along that of the transmission line. From this equation you can understand V is independent of omega. Now here the characteristic impedance for that of the lossless transmission line is under root of L by C only. L under root of L by C is the characteristic impedance for that of the lossless transmission line. Okay, now actually here we will see that what is the voltage standing wave ratio and what is the concept of voltage standing wave ratio. Now here actually there is the equation for that of the voltage we have written, and then equation for that of the voltage V plus e to the power of j omega L 1 plus V minus divided by V plus into e to the power of minus j 2 times beta into L. Equation for that of the voltage actually V minus divided by V plus is nothing but the reflection coefficient, and therefore the equation for that of the voltages is this one. This is the equation for voltage, and then equation for that of the current. Now we have to see that the what is voltage standing wave ratio. Okay, now we have investigated some features of the standing wave which exist along that of the transmission line, because there is the forward wave and also the reverse wave. Okay, and because of this some other wave is formed, that is standing wave. It is not a traveling wave, therefore it is called as standing wave. Okay, now this is the equation for voltage and the current. Now I will show the diagram that how just voltage is changing along that of the transmission line when it is minimum and when it is maximum. Okay, now if you observe the equation for that of the voltages and the current, there are the two terms. Okay, now first term is having the magnitude 1, second term is having a magnitude of reflection coefficient. But for the second term, the phase is changing. Okay, now the phase is changing, and the phase is nothing but phi L minus 2 times beta L. Okay, now phi L is the phase at the load. Okay, and at the load we have considered, and therefore here the phase is changing, and as the phase changes the voltage will becomes, and it will depends upon that of the L. Okay, if the L is changing, your phase is also changing, and therefore the resultant voltage and the current along that of the transmission line is also changing. Okay, as I move towards that of the generator, L is positive. Okay, now actually when I'm moving from that of the generator to that of the move towards that of generator, from load to that of the generator, L is positive. Okay, now we have drawn the diagram for that of because at the load location, that is location of the load is for Z is equal to for L is equal to 0, means your load impedance is located at L is equal to 0. Okay, now if you move from that of the load to that of the generator, L is positive, means that L will becomes 1, 2, 3, 4 like this. Okay, as you move from that of the load to that of the generator, means L is positive, then what happens actually, this phase is also changing. And if the phase is changing, then what happens actually here, this is the reflection coefficient, this is the phasor form actually, or and this is the one, means that first term represent its magnitude is 1. Okay, now the second term is this one, and this second term is reflection coefficient. Okay, now this reflection coefficient magnitude is moving along this circle. Okay, so that what happens actually, when it is aligning to the this line, your voltage will becomes maximum. When this reflection coefficient is reverse, or the direction of this vector is in the reverse direction, at that time this voltage will become minimum. This is the resultant voltage. Okay, now this resultant voltage is the sum of these two terms. Okay, that is, this is the one of the vector, this is another vector. Okay, now this vector direction is changing with respect to that of the L, and therefore the magnitude, this resultant magnitude is also changing. Okay, therefore the maximum voltage, there is you will get the maximum and minimum voltage along the top of the transmission line. At the same time, you will get the maximum current and the minimum maximum current and minimum current. But actually what happens, when you will get the maximum voltage, you will get the minimum current, and when the current is minimum, voltage is maximum. Okay, now this will happen along that of the transmission line. Okay, now this is because of the this phase changing. Now for that of the odd multiples of pi, then V of L is the minimum. Odd multiples of pi means the pi that of the 3 pi, 5 pi, 7 pi. For this phase, you will get the minimum voltage. At the same time, the current is maximum. At the same time, current is maximum. And for that of the even multiple of the pi, you will get the voltage maximum. Even multiple means pi, 2 pi, 4 pi, 6 pi. For all these phases, you will get the maximum voltage along that of the transmission line. At the same time, you will get the minimum current. Okay, now if you plot the voltage standing wave ratio, then you see that here L is equal to 0 as L increases, and this is your the voltage and current. That is the common axis we have used for that of the voltage and the current. Now this is this line, that is, this is your voltage, standing wave of voltage, and this another wave which is represented by dash dash line is the standing wave for that of the current. Okay, now if you observe it properly, actually when the voltage is maximum, the current is minimum. Okay, now here current is maximum, voltage is minimum. Like this, here you will get the maximum and minimum voltages along that of the transmission line. And we have to find out the location, where is the maximum voltage and where is the minimum voltage, what is the distance of the maximum voltage, what is the distance of minimum voltage from the load. Okay, now this is about the type of voltage standing wave ratio. Now for this, you can see that odd multiple of pi, voltage is minimum. Okay, now therefore we have defined, there is also, when the impedance maximum voltage, maximum impedance you will get, when the voltage is maximum, at the same location there is also the maximum impedance you will get, and which is the real value, and that value is given by this R max Z naught in bracket 1 plus reflection coefficient divided by 1 minus reflection coefficient. Okay, whenever the voltage is minimum and the current is maximum, at that location you will get the minimum impedance. At the, you will, if you measure the impedance at the that location, particular location, you will get the minimum impedance, and this is given by this equation. Okay, if you know the reflection coefficient at the load and characteristic impedance, you can also find out the R minimum along that of the transmission line. You can also find out the R max, which is the real value, not having imaginary value. Okay. Now, therefore, in this way, now this equation is useful actually when we are finding unknown impedance or when we are measuring unknown impedance. Okay. At that time, these equations are useful. Now, there is also the relation between that of the voltage standing wave ratio, and now we'll see that equations. Okay. Now, voltage standing wave ratio is given by, now we have obtained Vmax and Vminimum, and just when it is Vmax and when it is minimum, just we have substituted that phase angle value, and then you will get this one. And this is the ratio of the voltage Vmax divided by Vminimum, and you will get voltage standing wave ratio in terms of reflection coefficient. It is equal to 1 plus reflection coefficient divided by 1 minus reflection coefficient. Okay. Now for that of the lossless line, you will get the real value for reflection coefficient ZL minus Z naught divided by ZL plus Z naught. Okay. Now here we'll see that a short circuited transmission line, the reflection coefficient is 1, means total power is reflected back. When open circuited line, your reflection coefficient is also equal to same value, you will get 1. ZL is equal to infinity, means that total power is reflected back. Now when ZL is equal to Jx, that is the pure reactance. For this case also, when it is the pure reactance ZL, your reflection coefficient is also equal to that of the 1, and means that the total power is reflected back. Okay, now these are the three cases. Now VSWR value is ranging from 1 to infinity, and maximum value is infinity, minimum value is 1 for that of the voltage standing wave ratio, and for that of the reflection coefficient, maximum value is 1 and minimum value is 0. Now these are the relation between that of the R max and voltage standing wave ratio. Now R max is equal to Z naught into voltage VSWR. This is the VSWR, and R minimum is equal to Z naught divided by voltage standing wave ratio, because voltage standing wave ratio we can measure in the laboratory. Okay, and that is Vmax and Vminimum will be measured, and then you will get, we are moving that tap of that voltage measuring probe, so that you will get the voltage maximum and minimum along that of the transmission line, and then for it is possible to find out the voltage standing wave ratio in that of the laboratory. Okay, now R max, if you know the characteristic impedance, then you can also find out R max. You can also find out R minimum. Okay, and now actually that equation which we have seen previously was for that of general transmission line. Now for that of the specific transmission line, for that of lossless transmission line, what are the equation for that of the impedance transformation? This is the equation for that of the lossless transmission. Now here the alpha will not be there, only beta, because this alpha is 0 for that of the lossless transmission line, and therefore impedance transformation equation in normalized form for lossless transmission line will be this one, that is ZL bar cos of beta L plus J sin of beta L divided by cos beta L plus ZL bar sin of beta L. Okay, now this is the normalized form for lossless transmission line. Okay, now now one of the features, now what are the features exist, characteristic of impedance transformation relation for that of the lossless transmission line? We will see that, just we have to remember. Okay, Now actually the impedance, the character, the impedance along that of the transmission line is repeated after lambda by 2 distance. This is the first characteristic of that transmission line. The second characteristic is that the impedance at a distance of lambda by 4 is inverted. Okay, means that suppose that at distance L, the impedance is Z of L, then at distance L plus lambda by 4, the impedance is 1 upon Z of L. Okay, now this is the second characteristic which will be the this is one of the real fact you can say that for that of the transmission line. Okay, now the impedance is, we can say that in one sentence, the impedance is repeated at after lambda by 2 distance and impedance is inverted after lambda by 4 distance. Okay, and now then these are the properties which are used to finding the impedance transformation which can be match the impedance on transmission line. Now the matching condition, matching condition, impedance matching condition on transmission line. If the line is terminated with that of the characteristic impedance, we can say that the this is the line is matched. Or ZL is equal to Z naught means actually ZL is equal to ZL by Z naught normalized form. It is 1. Okay, now that is Z of L is equal to it is equal to that of the 1. Okay, these are the three important characteristics. Okay, we have seen that is first one is impedance repeated after lambda by 2, impedance inverted after lambda by 4, and for matching condition the total power is transferred to that of the load, or normalize the form, the equation for Z of L is equal to 1. Okay, now then there is uh, okay, now if you see the syllabus for of this one, that is the impedance matching, impedance transformation, we have seen that. Okay, and now we see that the Smith chart actually, now power that point is not mentioned. Okay, that is the power delivered and okay in your syllabus, and therefore we will not discuss that one. We will discuss the directly that Smith chart. Okay, and also Smith chart we will discuss now. S parameter, that is S11, S21, S22. These are the scattering parameters actually. From this parameter actually we can understand about that of the power, about the power reflected, power absorbed from a specific ports. Okay, and this is possible by using that of these S parameters. Okay, now here we will discuss the Smith chart. Okay, now Smith chart consists of the two types of the circle, that is the R circles and reactance, that resistance circles and the reactance circles. There are two types of the circles are available on that of the Smith charts. Now if you think about that of the resistance circle, you see that if you, this is actually the reflection plane, okay, reflection plane and reflection coefficient plane, because we are transforming the impedance plane to that of the reflection coefficient plane. Okay, now therefore this is the reflection coefficient plane, and this is the imaginary part Ju, and this is the real part. Okay, now the circles R is equal to 0 circle is passing through that of the center of the Smith chart. R is equal to infinity means if you are moving from left side to that of the right side, then that circle size will be reduced. Okay, and here you will get the circle of radius R is equal to infinity. Okay, now these circles are called as the resistance circle. Now, if you move along this resistance circle, you will get the different reactance value. The resistance value will be same. You will get the different reactance value. Okay, now this is the R circle. Now this is R is equal to 0 circle is the big circle. Okay. Now this is R is equal to 0 is the big circle in that of the Smith chart. R is equal to R is equal to 1 is the circle which is passing through that of the center of Smith chart. Okay. Now and this is here R is equal to infinity. Now this is the R circles. Now first of all we will see that how many construction how the Smith chart is constructed. Now then there are another type of the circles are also available. Now on that along that of the Smith chart is the this is the reactance circles. Okay. Now we are considering only the part of that circle which is inside of this R is equal to 0 circle. Okay, because this part we are not considering only because this is out of the circles or it's not a bounded value we have to consider here. Now these circles are called as reactance circles. Okay, you will get the different reactor circle. Now you can see that here the reactance circles for this is the x is equal to infinity, x is equal to 0 circle, x is equal to when x is equal to 0 means that actually it will be just the horizontal line we will get. Okay, and if you move towards this one, then you will get the positive value. Okay, and here downward direction negative value for that of the x. Okay, now here uh, it is x is equal to 0, then 0.8, 0.9 like this. Then here you will get 1. Okay, here you will get actually the infinity, x is equal to infinity. And if you move uh, downward direction, then these values are minus. Okay, and here minus infinity you will get. Okay, now these are the reactance circles. Now then for positive load inner part of R is equal to 0 circle. Now here actually you can see that now to locate the impedance along that of this Smith chart, first of all we have to normalize that impedance and then we have to select the point of intersection of R circle and X circles. Actually R circle means when you are impeding, when you are normalizing that impedance, you will get R plus JX. Okay, or R minus JX you will get. That R means that is the real part and that for that R we have to determine or we have to identify that circle. Okay, and for X also we have to identify the reactance circle, and intersection of these two circle is nothing but the location of that impedance on the top of the Smith chart. Okay, now then here we have shown this is your R is equal to 0 circle. Okay, okay, now this is your X is equal to 0 infinity circle for reactance. Okay, we can locate the normalize the impedance on that of the Smith chart, and that point is intersection by identifying the constant R circles and X circles, and intersection of these two circles is the location of the impedance on that of the Smith chart. Okay, Smith chart is nothing but the complex reflection plane. Okay, and to identify some special position of Smith chart, that is here this part is the R is equal to 0 and X is equal to 0. This is the short circuit point. Short circuit means that your ZL is equal to 0. Okay, now this point is actually it is this point on the top of the Smith chart is left extreme point is the short circuit point, and right extreme is the open circuit point. For this one, R is equal to infinity and X is equal to infinity. Okay, and this middle point or center of that Smith chart is R is equal to 1 and X is equal to 0. R is equal to 1 and X is equal to 0. That is now therefore point A is the short circuit point. This is the short circuit point. B is the open circuit point. Now then all the points lies on the top of the outermost circle. Pure reactance point is pure reactance point here. Actually you can see that this is the pure reactance point, positive, and this is the negative pure reactance point. Means that there is no real part. Real part is 0 for that particular point, and therefore we are saying that pure reactance point. Okay, all the points lies on the top of the outermost circle. Pure reactance point, pure lying on the upper half of R is equal to 0, represent the pure inductive load, or pure reactance is pure inductive upper point, that is the point C. Point C, you can see that here. Now I will show its image also, that is actually of that Smith chart, but it is same as that of that what we have described here. Two types of circles are available. Now the point C is the pure inductance point, and the location is R is equal to 0 and X is equal to 1. And the point D, which is the lower section, you can see that the point D is here. This is the point D, where R is equal to 0 and X is equal to -1. That is the pure capacitive point. Reactance is pure capacitive. Okay, when R is equal to 1 and X is equal to 0 is the matching point. Okay, matching point means Z is equal to Z naught. Okay, that means that is the center of that Smith chart. R is equal to 1 and X is equal to 0. X is equal to 0 is the straight line, horizontal line on the top of the Smith chart. Okay, and R is equal to 1 is this circle. This is R is equal to 1 circle, and this is the reactance circle, and therefore intersection point is this one, that is the matching point. R is equal to 1 and X is equal to 0. Okay, now these are some points, important point along the top of the Smith chart. Smith chart is the one of the way graphical representation of analysis of transmission line can be done by using that of the Smith chart. Very quickly, simple, and very quickly we can find out the unknown impedance at a specific location by using that of the Smith chart. Okay, Smith chart is nothing a set of constant R circles and X circles plotted on the top of the lens. Okay, now reflection coefficient at any point on the top of the transmission line is given by this equation. Actually, we have seen this equation. It is in that of the equation for that of the voltage and the current. Same equation actually we are using in the reflection complex plane. Okay, and now this is the actually we have already seen. VSWR means 1 plus reflection coefficient divided by 1 minus reflection coefficient. Okay, now analysis of transmission line using Smith chart, considering that the admittance is nothing but the inversion of characteristic impedance. Okay, that is the admittance Y is equal to 1 upon Z naught. Okay, now whenever there is the admittance, you have to find out, then you can also find out it. Okay, normalized admittance is G plus JB. G is nothing but the conductance and B is nothing but the susceptance. Okay, normalize the form. First of all, we have to find out. Okay, now here is one example actually. Use of Smith chart for that of the transmission line calculations. First of all, what we have to do, you have to normalize the impedance. Then you will get R plus Jx. Two circles give the impedance. Now this is the, here you can see that this is the X circle and this is your R circle, and this is the point of intersection. Here the you will get the impedance. Impedance is located on that of the Smith chart, and this is the theta L, angle of reflection, angle of reflection coefficient theta L at particular location. At particular location there is some reflection coefficient, and for that reflection coefficient some angle is also there, and which is nothing but this theta L. Okay, for normalized admittance, okay, now for normalized admittance actually these are the G circles. You have to use the same Smith chart, okay, to find out the admittance, but that admittance you will get opposite side of 180 degree on that of your VSWR circle. Now we will see that actually VSWR circle means what. Okay, now here, okay, now here how to draw the VSWR circle. Now we'll see that one of the example, find ZL at distance L from that of the L. One problem here we will discuss that. Okay, now this is the intersection point, and this intersection point is the you have to how to draw the VSWR circle. Just now I will explain here. Now this is the center of Smith chart, and you have located the impedance, that is the intersection of X circle and R circle, and this is the point. Now you have to draw the one line from the center of the Smith chart to the intersection of the point and extend it up to the outer circle. Okay, now then afterwards you have to take the compass, and you have to take this radius. This is the radius, and you have to draw the circle, and that circle is nothing but the VSWR circle. And to find out the VSWR at that particular location, just you have to find the value at this point, that is the intersection of horizontal axis, which is the real part of that reflection coefficient, and that VSWR circle will be intersect at this point, and you will get some value. That value is nothing but actually your VSWR or voltage standing wave ratio, and its value, this value is 0 and is infinity at this point. Okay, now actually along this horizontal line, the you will get the values which are ranging from 0 to infinity. Okay, now here is 0, here it is 1, then 2, 3, 4, 5, 6, 7 up to infinity. You will get the infinity here. Okay, now your VSWR circle will intersect to this horizontal line, and this intersection point is nothing but your VSWR. Okay, in this way, first of all, you have to draw the VSWR circle, and then afterwards, you have to find out the VSWR just by measuring the value at the intersection of horizontal line and VSWR circle. Okay, in this way you have to draw the VSWR. You have to find out the VSWR by using the this Smith chart. Okay, then you have to find out the unknown impedance at distance L from that of load. Okay, L from that of the load, or suppose that load is located at this point. This is the location of the load. Okay, you have to move some distance so that you will get the another impedance, which is unknown impedance along this VSWR circle. Now actually in this particular case we have to move the some angle. Okay, suppose if you want to find out the uh, unknown impedance, then you have to move actually 2 times beta into L. Now actually from this point, okay, from this point you have to move 2 times beta into L. L is also known to us. Beta is, suppose if you want to find out the impedance at the location L, then beta is already known to us. L is also known to us. Just you have to move this. Now, this 2 times beta into L, you have to convert into that of the degree. Okay, now actually, this total is total circumference of the circle is lambda by 2. Now this distance is also in terms of lambda also we can find out. Okay, now in tomorrow's lecture we will see that remaining part. Okay, today we will stop here. If you are having any difficulty, today we will solve the problem of this Smith chart also, and that waveguide means what is the antenna array, what are the and also problems of the antenna, monopole, dipoles. We will see that in the tomorrow's lecture. Okay, today we will stop here. If you are having any difficulty, you can ask. Okay. Actually, you can also send your details in the chat box. Actually, your name and your category also, because it is required. Because this we have to give the information about the participants. Okay. Therefore, you write your name, class, and category, OBC, open, SC, ST, or any. Okay, you write. You fill up this, all of you, please, because it is required. Yes, please give me the information of yourself. I will send the Google one form also to you. In that also you have to fill all this information. Okay, because this information is required. Okay, that's why. Therefore, I am. Please send your name, branch also, and class, branch, and category. Okay, because this is required. Yes. Okay. Whatever may be that, you can send, no problem. Okay. Your name also. Okay. Name, class, class, branch, category. Okay, today we will stop here. All of you, please write your information. You send information. Remaining, please. Okay. Okay, thank you. We will meet tomorrow at 5 p.m. Thank you.